So, change the subject totally. First of all, my co-presenter couldn't be here because he's neck deep in solving different problems at Oak Ridge, which is due to Oak Ridge. I think I paraphrased James when he says, they love our hardware, but they don't like our software. So yeah, exactly what he meant with that, I don't actually know, but obviously they have their own stack and they want to implement that and so on and so forth. This creates a little bit of a problem because it's a combination of our software. Anyway, John isn't here. He's also the guy who spends most of his waking time doing these benchmarks that I'm now taking credit for. I used to do benchmark way back when, but honestly, I can't be bothered anymore because benchmarking is difficult. Benchmarking is hard, but it's also boring if you have issues because you have to rerun certain things over and over again trying to figure out why things doesn't work. So I do want to talk a little about benchmarking, especially why we're doing the benchmarking all the time. And we actually run benchmarking daily, and sometimes several times daily, depending on where we are in the process. Now the biggest challenge we have is the fact that hardware keeps changing. Hardware keeps updating, which is good. But it also means you get new versions of ways of doing things. You get new architectures, you get new kernel versions, you get new network types, you get new tunables, and so on and so forth. So if you kind of look at some of the complexity we have here on the hardware, I mean, moving from an Intel platform, which we did earlier, to an AMD Rome platform, it was kind of no-brainer, right? You go from something with PCI Gen 3, limited amount of lanes, to PCI Gen 4, 128 lanes per CPU, great. Unfortunately, these chips are multi-chip assemblies, which means you have a NUMA processor in there that needs to be handled differently. And different file systems, or different versions of the file system, which say benefits from different ways of doing that tuning. So we actually have to go through every single step of the chain from the client side, over the network, to the servers, to the drives, and everything in between to find the right tunables at any given time to be able to kind of get the right performance out of these systems. And with right performance, I mean the best performance. Now the second part of that is that as we go on, as we iterate on and on, we need to make sure that we can maintain that performance. Because one of the things that may be debated, but one of the things we found that every time we have a new update to Lustre, every time we have a new client, every time there comes a new patch, the likelihood of actually having a performance regression is greater than, not having one. So we keep finding issues where those performance regressions need to be addressed to keep pushing the envelope of these systems. And the reason for that is not that we are that picky about a percentage here or a percentage there. But the worst question you can get if you are an architect like myself or support or what have you in a company is the fact that you have your customers calling you and saying, the file system is getting slower. That last update you did wrecked our performance. We can no longer hit the peak performances. Now that's sometimes subjective and not actually real value, but proving that is really hard. Anyway, I want to go through a little bit about some of the things we've done over the last couple of years and some of the results we have, just to give you an idea where we are currently. Now, the benchmarking is really also one of these things. Why do we do benchmarking? It's because we need marketing numbers. Well, marketing numbers can be made up, and most people make them up any which way, so it doesn't really matter. So it's all about how can we get specific results. Now, the customer benchmarking, when a customer comes to you with a set of requirements, those are, I wouldn't say easy, but they're well defined. You know how to do it, and you know how to get the best results, and you can do that consistently. But when you have a product that evolves over time, you get new firmware and so on and so forth, maintaining that and proving that you can maintain that with different tunables is really the main reason we're doing all these things. Now, what are the technologies to use? We have IO500. IO500 is supposed to be, oops, that was actually one too many. Well, it's funny. It has a life of its own. IO500 is supposed to be kind of the top 500 of storage. I was actually involved in the creation of the first IO500 way back, but I kind of split from the team because we couldn't agree on the hows. And one of the problems I see with i500 is the fact that it's not limited to production systems the way it is in top 500. That means you can create a Frankenstein system that can get some fantastic results, but has absolutely no validity in real world. And that kind of makes the whole process default. That's why you won't see any HP systems on that list, despite the fact that we could score high on some of them. Some of our customers have made their systems available on the i500, but we are taking a stance against that because we don't believe that's the right way. You also have the problem that you have some of these tests, like the 10-node cluster. Well, we can't saturate our storage with 10 client nodes, no matter what we do. We need more. So it will also always show some of the stuff we do in a bad light. So we're going kind of old school. We've taken the latest versions of IR, the latest versions of MD-Test, the latest version of FIO. Sometimes we do IO-Zone as well. And we use the settings that we can. In some cases, we actually modify it to be able to scale to the right size. I mean, D&E and being able to scale MD-Test to 20, 30, 40 MDTs have been a challenge, just to put it very lightly. So all of these things we do, but we also try to be consistent over time. And that is really the biggest challenge we have in where we're going with the, kind of these things. And again, the challenge is consistency. Now, our test environment is not the greatest. We don't have unlimited nodes. We don't have unlimited systems. All our systems is essentially about 20, 21 nodes of PCI Gen 4 based clients using whatever network is supported at any given time. And the networking part is actually a different issue as well, because we currently support 3 different types of networks with 4 different types of settings. And that being obviously InfiniBand, which everybody kind of knows well and know how to optimize. It is Ethernet running on Mellanox hardware with either Rocky or TCP. And you might wonder why we do TCP at all, but that has its uses. And then obviously we have the Slingshot, that is our own version of the Ethernet fabric that has totally different ways of working, despite the fact that it is Ethernet. And all of these things need to be done for every single version of the code we do. And that's also part of the challenge. And it really comes down to how can we show that the numbers are consistent over time. Now, we've also done a lot of work with software Rocky, where you actually are running a hardware Rocky on a Mellanox NIC in Ethernet, and then you'd run the Rocky on the clients in software. And that's the reason why we had to do that, because some of the protocols we use doesn't have all the bells and whistles that it needs to be at any given time. And we now can show that actually software Rocky can match hardware Rocky, despite the fact that we use about 5% of the CPU capacity to get there. So it is not pain-free, but it can be done. And that's kind of where we are at the moment. Now, our test rig, apart from the clients, which are fairly standard, is based around the latest generation of our hardware. And it's really, not that unique type of hardware. The nodes we're using is actually dual node systems, each with an AMD Rome CPU, sharing the drives, whether we're using that for our management unit, for our metadata units, or for our disk server units. And the disk units we use are your standard Seagate 106 drive enclosures, the same as everybody else is using pretty much in the industry today, the highest density you can get from a disk drive. So that's kind of our building blocks. Over the years, we've had a number of releases of our software stack, and I've picked 3 here, which is the Neo 4.1, which is the one that debuted with the cluster solution back in 2000, essentially when we started bringing that to market. The 4.4, which was the latest, I would call it, main release of that one. We actually have 4.5 out now, but it's more for fixes and other things. And the 6.1, which is where we went to Lustre 2.15 and a newer kernel. Now, that seems like an easy thing to do, moving up to a new kernel and at the same time moving up to a new Lustre, but tell me that's been painful. Not just because Lustre have been actually late, Lustre 215. I mean, we expected it in December last year, and then it got moved to January, and then to February, and so on and so forth. For obvious reasons. There were bugs in it, serious bugs. I don't know how many data corruption bugs we saw in corner cases. Not off the bat, but in corner case. When you did a failover and a failback immediately, suddenly you got data corruption in some cases. Really hard to debug, really hard to fix. But we went through that, and I think the entire community went through that in different stages, just to get it stable. Because the one thing we don't want to do is get a system out, and the first thing you do is trash the file system or the data of the customer. That's not a good way to keep a happy customer, right? So we went through a lot of these things. So just remember, when we speak about the different versions, and you see we go from Lustre 2.12.05 to Lustre 2.12.4.3, and then we went to Lustre 2.15. We actually still shipping a version based on the release candidate 4 because we haven't really gotten all the last bits and pieces in there yet, but it is essentially the full release of the version we are shipping today. So when you see the numbers 4.1, 4.4, 6.1, those are the kind of things you need to remember. I couldn't be bothered to put that on every slide. Now, with this hardware, with this technology, what do we actually do when we look at these things? Well, we look at a lot of different tests. Obviously, we do both direct I/O and buffered I/O because some customers actually use direct I/O because they have control of the application. Some are commercial customers, usually do buffered I/O. So this is kind of a mix of those two. We use both fixed time and fixed data. Fixed time, we think, is still the right way to do things because it shows the consistent throughput of an application or a system when you load it fully for 4 to 5 minutes, which is how long we run these tests. But in some cases, you get fixed data requirements, and you always have the problem that you have a tail end because the clients are never equally fast, despite the fact that they are identically from a hardware and software point of view. Some clients will always have a tail that kind of gets your total results down a little bit. But we still do it for consistency. One thing that's important is between every single test, we flush all the caches to make sure that we are in a pristine situation. Because otherwise, you can get a lot of variability over time. We also run these multiple times to make sure that they are always consistent in the results and we don't have too much variability in the results. We also run IOPS. Not that it's really that important on disk systems, but when you're trying to make solutions that goes into specific machine learning and AI type solutions, IOPS is really all the rage. They rarely have throughput that requires the modern systems. I've seen some of the large benchmarks, even with GPU direct storage, that's supposed to get some fantastic numbers, but in real life, when you actually run inference, they're hitting like 10, 15, 20 gigabytes per second, but they may be hitting 1 million IOPS. So it's really a trade-off between those two, so we also need to do that. And then obviously the metadata, which is a challenge as well. As you probably heard, some of the new systems out there have requirements for sustained file crates in the millions of files per second for up to 5 to 10 minutes at a time, which is a big challenge for Lustre file systems today. So we spend a lot of time on that as well. And obviously we do the standard ones like ODB survey, just to make sure the backend works and that self-test, just to make sure that the network is always in a pristine solution. But that's kind of that's kind of the standard steps we go through. As I mentioned, we run all of these tests, and we do this fully scripted. So that means we throw in one of these sweeps, and it takes almost 2 days to run a full sweep. And then we reformat everything, and then we throw some other data in, and we do it again, and do it again, and do it again, and collect all of these data. So just to give you an idea about what we've been able to do in some of these cases, when you look at an all-flash array, this is 2 OSTs used in parity clustered array. Tuning parameters has, in some cases, you can see, gone up by different numbers, but depending on which of these tests we see. It's not uniform by any means. And in this case, specifically when it comes to throughput, this is not a result of Lustre 215. Lustre 215, when we started with this, had actually had some significant performance decreases. It was actually 20% slower than Lustre 212 in the early tests. That wasn't me. So we've seen some interesting things. Now, every time we do one of these, we come up with a new set of tunables. Those tunables are added to a system with its updates. So it's not something that anyone does locally. It's all handled by Puppet, so nobody has to go in and set those tunables, because we don't think that users should actually have that control. That doesn't mean that some don't change things, but we try to keep it on a level basis, because not all our customers are Oak Ridge or NERSC or what have you. Or in Europe, I would say CEA and CSS, or Lumi for that matter. Other numbers is a little bit more modest, specifically on the HDD type systems, because there's not really that much headroom you have in those systems. Most of the performances you get out of an HDD system is limited by Gen 3 SAS. Especially when you have 106 drives in an enclosure, you're really limited by how much SAS performance you can get out of these systems. So that's about it. That was one of the things that was interesting. You see, it's modest for most of these things, with the exception of file stats when you do a single MDT. And this is one MDT, MDT0 or MDT1, by the way. They actually produce about the same thing when you run them separately. If you run actually DNE2, which striped directories, you actually see a certain performance hit that is not necessarily nice all the time. It could be up to 20% in some cases. But the file stats, which essentially is IOPS optimization, that's really due to the new kernel and how it handles the NVMe drives we have in the systems. Same thing with single stream performance. Obviously, there's some significant enhancement in single stream performance on Lustre 215, which is obvious here, with one exception. The buffered writes with fixed time, the buffer writes with fixed time is not affected that well. We're still figuring that one out, because why are the other three showing us, up to 100 or even higher on 100% performance, when that single one doesn't? So there's some weird things going on. And we've spent a lot of time doing that, because we now have customers requiring a minimum of 2 gigabits per second single thread reads or single thread writes, which is sometimes hard to achieve. We also have some other interesting customers that require that all benchmarks should be run with 50% reads and 50% writes at the same time, which is something Lustre is not really good at, unfortunately. At least not when you benchmark it. So that's also some of the challenge we have. Now, I probably have 300 more slides on these enhancements and so on and so forth, but I do not want to bore you with too many data. But what I do want to do is show you a couple of things comparing the 3 RDMA type solutions we have today, which is InfiniBand, Ethernet with Rocky, and the KFI or the Slingshot protocol with different things. I did throw Ethernet with TCP in here, and as you can see, TCP is crap. And that's due to a number of things. First of all, these nodes all have 200 gigabit interfaces. And when you run TCP, even if you run it in bonded mode, it will only actually use one of them. So it's really hard to get full performance out of that for writes. Reads, it's not that bad. But what is important here, what I think is really the big message, is that regardless if we're using native HDR InfiniBand or 200 gigabit Ethernet with Rocky, or KFI, which is also 200 gigabit with built-in RDMA from the libfabrics, we're getting essentially the same results over the board. So hitting about between 58, 59, up to 63, 64 gigabytes per second write on a single array. That's 2 OSTs, 24 drives. And we can do this consistently. The writes are hitting north of 80 gigabytes per second, again, consistently all over the range. And we've done that for quite some time. So those numbers are kind of interesting. Now, what's also interesting, which is something that everybody's been struggling with, it's a well-known fact, is that IOPS is not that great. Take a look at the IOPS. So these are 24 drives delivering write IOPS in the 85,000 range. Now remember, a single drive can do, about 700,000 write IOPS on a single drive. But as soon as you apply RAID on top of these, the bottom falls out totally. And that's something we're still struggling with, and a big issue with anything that has to do with RAID. It's not a Lustre issue per se, it is a RAID issue. And you can see the reads are 1.2, 1.3. Now, if you really need good performance on IOPS, you have to go to RAID 10, because the overhead is much less there. I don't have the numbers here, but the write IOPS for RAID 10 is north of 1 million. And read IOPS is north of 2 million. So, if you really need good performance for IOPS, it has to be RAID 10. You cannot do it with parity cluster RAID or RAID 6. Oops. New feature. We did the same thing with the disk systems, and you can see we either are using single JBOD or dual JBODs. Now, dual JBODs is where we peak a little bit on these systems, but you can kind of see from a write performance, we're hitting a good 35 gigabytes per second in most cases. Read is about equivalent on these systems. So, not bad numbers, and again, consistently over the board. Now, if you look at metadata systems and look at different versions of doing that, the results for 32K with or without DOM is pretty much the same as well. So you can kind of take that as a limit. And you can see a single MBT can now do about 155,000 write IOPS. Again, these things tend to be CPU frequency based, but we use the same CPU for everything. So the one that really stands out is stats. In 215, stats has really jumped up and are hitting north of 600,000 consistently, which is really good on these systems. That's something we've seen from others as well. But 215 really helped the stats. It hasn't really helped the other ones that much, but it has helped stats a lot. Now, the one thing we haven't talked about here, and I can see James smiling down there, is that all of these things on LDiskFS. I haven't shown you a single data on OpenCFS. And why is that? OpenCFS sucks. Well, from a performance point of view, it is really much slower, especially on IOPS, than LDiskFS is. It has a lot of other values, obviously, but when it comes to performance, it's really hard meeting these numbers with OpenCFS. Now, we've done some changes, for instance, going from NPS 2 to NPS 1 for OpenCFS. That gave us a 30% increase in disk-based IOPS, or I/O, not as much on the flash, but we're still trying to optimize that. Every time there's a new release of OpenCFS out, we're trying to implement that as soon as possible. And we are seeing, I would call it, incremental increases in performance as we go to the, I think we're either 214 or 215 at the moment with OpenCFS. But it's still way behind LDiskFS, which is an issue. Again, same thing, comparing in this case, comparing TCP with the other one. So I won't go into detail. I kind of want to get to the final point of lessons learned a little bit. Changing architectures on the server side is really difficult. You have to learn so many new things about the tunables, how to set it up, how to get performance, how to even get multiple I/O cards working in console with each other, which is really, really difficult on these systems. And that's also something that we've been going through a lot. Now, this unfortunately requires frequent work with your developer of the hardware stuff, because the firmware stuff you get, or the firmware versions you get from version 1 or version 2 of these things, is not even, I wouldn't even call it debugging versions. It's barely functioning hardware. And every time we get a new update, again, we get better software, we get better firmware, and we get performance regression that needs to handle some way or another. So it's kind of an iterative process we've learned. Now, we also learned that NVMe from one vendor and NVMe from another vendor is not the same thing. We've been using Samsung, we're using Kioxia. Initially, Kioxia was about 15 to 20% faster than Samsung. And none of them could really explain why. It's just what we found. Then we went to Rocky Linux 8.4, and suddenly they were on par, without any other changes. Go figure. But I mean, those are kind of the learning process you go through. Keeping up with Linux enhancements, as I said, we're still on Rocky Linux 6.4. We haven't moved to 8.6. We're not 8.4. We're not moving to 8.6 quite yet, because every time they come up with a new kernel version, you have to start over again, test everything from scratch with every single parameter to figure out how to get it close. Because again, you upgrade, you have a performance hit. And then obviously, newer version of everything will affect the entire ecosystem, right? It's not just a rip in and replace and you're back to where you were originally. It's not like replacing a faulty component and you're back to original performance. It is, again, a performance hit usually. So doing these benchmarks, doing it over and over again, is really key to maintaining predictable performance of the systems. So some of these numbers is just the fact that we've been able to tune a lot. 2.15 has been a big boom. Once we got it stable, once we got to figure out that the tunables had to change, and the default values for tunables in the system rarely works that well. There is a slide in the deck that you can look later on. You can see what the default values are and what we actually use, which is usually many times higher than the defaults, because that's the only way we can push these systems. We also found that the difference in RDMA that used to be obvious back in the CentOS 7677 timeframe is essentially gone. We can get the same RDMA results regardless of what fabric we're using, whether it's InfiniBand or Rocky or Ethernet or even KFI nowadays. So that's something that's good. That means it's predictable. TCP still requires a lot of work, but we still believe that with a little bit more, we can actually get close to where we need to be. But it's really one of those issues that is it worth spending time on it or not? You'd be surprised how many commercial customers are still doing TCP and do not want to do Rocky. I haven't figured out why yet, but there are some, old school defaults that they hardly change. Now the final one is really the important one, and this is my final slide, so don't worry about it. Is can you keep these, or can you actually achieve these data in the field? Can you actually get the same results that you get in the lab on a customer system? Actually, you can, if you have full control over everything and know exactly what you're doing. And some of our benchmarkers, who are a lot better than I am on this, are spending their entire time doing exactly that, trying to get things out. But most often, the expectations is higher than the deliverables. That's why we never actually quote full performance to a customer. They never really actually see some of these data outside publications, because these are hero numbers. Reproducible hero numbers, but hero numbers. Because, in the field, things will change. The number of clients will change. The oversubscription of the fabric could be different. The specific version of the clients could be different. I mean, if you're having clients running on something else than a Red Hat version, like an Ubuntu client, for instance, you will see different performance results, and so on and so forth. So we always make sure that we hedge our bets by at least 20% in the field, because it's better to under-commit and over-deliver than the other way around. So that's kind of a long story to say that we're fairly comfortable with doing the benchmarking and the numbers we present both publicly and internally. But it is a nightmare trying to keep this up over time. And we have a fantastic benchmark team at HP that obviously split the time between doing customer benchmarks and making sure that all of these different versions work, especially on the big mainframes. So benchmarking is a necessity, but it's boring as hell. Thank you.
Any question?
During benchmark, do you also remount the file system or format it to get back to the best performance? Or because I know that if you are benchmarking the same file system for days, at some points you need to at least remount.
Right.
To get those hero numbers.
So one of the things I didn't mention, for instance, on the flash systems, every single run is interrupted with a trim in the between to clean things up. As I was saying, we run a lot of different versions of the OS. So I would say that these benchmark systems are probably reinstalled from scratch once or twice per week. So it's not running the same file system for months at a time, because we know there will be degradation of performance over time as it settles in and you have subtle differences underneath. So we do that as well. But we only have a limited number of systems, and they do get reformatted ever so often because we have to upgrade something. And we'd rather reinstall from scratch and just patch it, because obviously you get better. And then you have the problem of wear and tear. Drives will wear out. You lose a drive in the middle of one of these runs, and you just have to scrap that, replace it,
that's
go
the
back.
worst when you have like big file system. You cannot rely on the drives. At some point, there is always one drive putting some mess.
Well, let's talk to the Western Digital drives. I mean, they have a mean time between failure of 2 million hours. That means they never fail. There's 33 years mean time between failure. So a drive never fails, right? Well, drives do fail. And then we have problems with cables. And then we have problems with power outages. And then we have... Yeah.
Any other question?
Yeah, this was too boring, so nobody really...
No, I have one for you. A quick dive question about your CPT configuration. You mentioned that you have an increment from the switching from NPS 4 to NPS 2. I'm wondering if it was not due to this modification. I think it's due to the modification of CPT.
Could be.
It's just a question, because with the RAM CPU, you have 4 CCX and 4 memory controller. And if you spread correctly the CPT on each internal CCX, you will have a full memory bandwidth. It's just a question because...
So basically, we run CTP of 8 on everything we do. We found that has been our most consistent results. But yes, we've mixed around with that as well. We tested all the iterations of that. But CTP of 8 seems to be the most efficient. NPS of 2 for flash, NPS of 4 for disk, and NPS 1 for OpenZFS seems to be the fastest at the moment. But again, we don't trust these numbers consistently, right? We retest it because things will change, and you get a new piece of firmware and things will change, and so on and so forth, right? So repeating, kind of wash, rinse, repeat thingy is something you need to do consistently, and one of the reasons why we spend so much time on it.
Okay, thank you. Any question?
I'm not sure if I have a question, but it's a good comment to this thing with the performance degradation over time on production systems, that you can never, if you do a benchmark 2 years in a system's life, you cannot expect to have the same numbers that you started with at when you procure the system.
Right.
And it's for us as admins, it's sometimes difficult to explain to my management that why do we have poor numbers now? Why isn't this numbers the same as when we bought the system? Well, they don't understand this thing. Well, this file system is 80% full now. It wasn't when we started, stuff like that.
So I agree with you. So I mean, we've actually done those kind of benchmarks as well. What happens with a file system 80% full, and how much degradation do you really have of performance? and so on and so forth, because I mean, the right question from a customer is that I want this performance, and I want it at 8% full or 90% full. That means that it sets the bar for what you need to do. Now, one of the things that is hardest for us is the file system slower now because you've added a lot of data to the system, so it's full or semi-full or whatever. Could it be fragmented, which we also seen at times. But more importantly, when you apply an update and somebody pays a little bit more attention to the file system, and then says, oh, this update made it slower. And how do we prove that it didn't? So initially, a while back, we actually spent about 1% of the outer rims on all drives and created a separate file system on those, what we call benchmark file system, so that you could take the new version, unmount your actual production system, mount that outer sector things, and run the benchmark. And it would be just as good or better than the original ones, because that's essentially an empty file system on the outer rims of disk drives. On flash, it doesn't really matter where it is at, but the same concept applies. There's kind of a set of unused sectors that hasn't been submitted to that much churn. So we could show that the performance was consistent with the initial data. Now, that's become less of an issue lately, because I think the understanding of file system performances have increased significantly in many customers, and maybe not the manager side of things, because they never understand the technology any which way. But at least within the admins around the world, that a file system that's been in use for 6 months, 12 months will be slower because of a lot of features. Now, you could reformat everything, and it will probably regain its original performance. But you rarely do that. So it's really just showing empirical data, and we have a lot of that, and I think every other vendor in the market has that kind of empirical data showing that, over time the hardware itself doesn't get slower. There may be other factors hitting the media that makes it slower. And one of the biggest challenges that's been lately is, how do you do trim, for instance, on flash? Because trim can really, murder your performance when it's running in the background. If it runs consistently, if it runs opportunistically, or if it just runs on a cron tab every now and then. It's one of those things that's really hard to do. And you can either do that externally, or you can do that for Lustre, which also has some issues as well. So there is a lot of component to this equation that is really hard to put into a simple statement or a simple document, whatever you want to call it. And, I don't think there will ever be a good answer to management of this system is now performing at this level, which is expected. If they're good management, they would just, listen to you because you know better than they do about what the file system is supposed to do. But we do have that occasionally from different types of customers. And it just, you have to have a discussion, go into details, explain why things are getting slower. But you can never guarantee a file system will work at a certain performance through life. And that's always a discussion you need to have to set the expectations, especially with the disk-based file system, obviously. But even with flash system nowadays, you do need to set that expectation correctly.
Thank you, Torben.
Thank you.